Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 2.2, day 2, entitled Graphs of Functions. And today we're going to talk more about the vertical line test and equations that define functions. And the vertical line test is a really easy way to figure out whether or not a graph represents a function. And basically what you're going to do is you're going to have the picture of your graph. Let's make a line here. And then you're going to draw a vertical line through it. And as long as that vertical line only touches the graph one time, then that graph is a function. So the definition here says that the graph of a function exists if and only if no vertical line intersects the curve more than once. So if you have a circle, for example, and you draw a vertical line, that vertical line is going to touch it twice, so that circle is not a function. So here we have some other examples. Okay, here we have a curved function, and there's our vertical line, and that vertical line touches the graph one time. No matter where we put that vertical line, we could draw all kinds of vertical lines going across this function, but still those vertical lines are only going to touch the function one time. Now on this other picture, we have kind of a loop here in this graph, and they have that red dashed vertical line going through it, and you can see that it hits the graph twice. So this is not a function. And again, we could put that vertical line in other places. Sometimes students say, well, what if I put the vertical line over there? Well, yeah, it passes at this point, and at this point, and at this point, but once you get here, then you end up with a situation where you're hitting the graph twice. So if that happens at any one point in the graph, then the whole function fails. So in order to pass the vertical line test, you have to pass everywhere that you put that vertical line, not just at one or two specific points. Okay, so if each vertical line, x equals a, intersects the curve only once, then exactly one functional value is defined. But if a line intersects a curve twice, then the curve cannot represent a function because a function cannot assign two different values to a. So basically what that is saying is, if we go back and look at this previous picture, that means that I have one value for a that I have put into this function. So this function must be f of a. So I put f of a into the function. I put a into the function f, and I got b out. And then I put a into the function again, and I got c out. So that would be like substituting 1 into an equation and getting an answer of 5, and then substituting 1 into an equation and getting an answer of 6. That can't happen. If you put 1 into the function and you get an answer of 5, the answer is 5 every time you put 1 in. Okay? We've talked about like our vending machine and our pop machine analogy before. So this would be like pushing a button for Pepsi and getting a Pepsi, and then pushing that same button for Pepsi and getting a Mountain Dew. That can't happen. It's not supposed to happen. The machine's not supposed to work that way. So it's not a properly working function. Okay, so in example 8 here, they've given you some curves, and they want you to test whether or not they are functions. Okay, so for part A, we have a graph of a circle, and they've already drawn in a vertical line for us, and we can already see that that vertical line is going to touch the circle twice. So no, that graph does not represent a function. So there's a good example where you can have an equation of a circle, but that equation is not a function. Okay, and for part B, if we drew in a vertical line, no matter where we drew that vertical line, it would only touch that graph one time. So yes, that graph is an equation that represents a function. Same thing for C. Okay, this one is a little more rigid. This one could be a piecewise function, perhaps. But no matter where we drew our vertical line, we would only touch that function at one spot. So yes, this is a function. But for part D, we have another curve here, and they've drawn in a vertical line, and you can see that that vertical line is going to touch that function 3 times. So no, that graph does not represent a function. Okay, so now we're going to take a look at some equations. And instead of looking at the graph of the function, we're going to look at the equation to figure out if it represents a function. Okay, so any equation in the variables x and y defines a relationship between these variables. So if you have the equation y minus x squared equals 0, that's defining a relationship between x and y. But the way that we need to figure out if this is a function or not is basically what's highlighted down here at the bottom. We can see that the equation defines a rule or a function that gives one value of y for each value of x. So what we're going to do is we're going to take this above equation and we're going to solve it for y. So you would add the x squared over. And then hopefully you realize that this is a parabola. So any value that we plug in for x is going to give us one value out for y. So I'm not going to have any situations where I substitute in a 1 and I get a 5 and a 6. When I substitute in 1, I'm going to get 1. When I substitute in -1, I'm also going to get 1. But that's okay. I have every value in my domain has its own value in the range. So one value for y for each value of x. That's the definition of a function. And since it is a function, we could rewrite it with function notation. Instead of y equals, we could just say f of x equals. Okay, now example 9 then, we have two equations here, and we're going to see if they are functions. So what we're going to do is we're going to solve for y. So that's what you need to think when you see these types of problems, is you need to solve for y and see, like it said on the other slide, if there's one value for x goes to each value for y. So for part A here, if I was going to solve this for y, I would have to add the x squared over to the other side. So I would have y equals x squared plus 2. And this is going to be a parabola. It's going to open up. It's going to have a y-intercept of 2. And every value that we plugged in for x would give us a unique value for y. So yes, this is going to be a function. And I believe there's a picture on the next slide, and you could test with the vertical line test as well, but this one is going to pass. Okay, now for part B, if I try to solve this for y, I have to subtract the x squared over, and then I'll have y squared equals negative x squared plus 4. And then I'd have to take the square root to get the y by itself. Now when I take the square root, remember, I get a positive and a negative value. So right away, that should be a little clue that there's an issue, because this means when I plug in a value for x, I'm going to get a positive answer and a negative answer. I'm going to get two values for my answer for y for the same value that I plug in for x. So this is not going to be a function. And hopefully when you look at that original equation that they gave us, hopefully this format looks familiar. That's an equation for a circle. That's x plus 0 squared, and then y plus 0 squared equals 4. So it's a circle at 0, 0 with a radius of 2. And here are the pictures for them. So again, for this parabola, we can see that here's the parabola of the graph after we solved it for y. And if we draw in a vertical line, again, no matter where we draw in that vertical line, it's going to pass the vertical line test. That vertical line is only going to touch the graph one time. But for the other equation, the circle equation, since we have a circle, anytime we put in a vertical line, it's going to touch that circle twice. Now technically I could draw in a line way over on this edge that would really only touch one point over there, but that's just at that one spot. Okay, so that's not enough to make it a function for every single other spot. So remember, if it fails the vertical line test in one location, then it fails for all of them. And then your book has a nice chart in it that has some of the commonly used functions that we'll see. So here are some linear functions. You've got your horizontal, and then you've got your slope lines. You have your different powers. You have x squared, x to the third, x to the fourth, and x to the fifth. And then you have your square root functions. So you have your square root, your cubed root, your fourth root, your fifth root. And again, anytime we drew in a vertical line, all of these equations would pass the vertical line test. It might look a little tight in some of these where that curve is, but none of those points actually overlap. They're all spaced enough that if you drew a line, you wouldn't hit more than one point. Here we have our reciprocal functions, which is where you're dividing by x to some power. So you get two little curves in either the first and the third quadrant or the second and the fourth quadrant here. I'm sorry, first and second quadrant. And then we also have our absolute value function. That's going to look like a big V, and that would pass the vertical line test. And so do step functions. Step functions would pass the vertical line test. I know at some places we could hit a solid circle and an open circle, but remember that open circle, it means that that number technically isn't our solution. So when we hit that closed circle, that would be the one point that we would hit that function. So those are all examples of functions that pass vertical line tests. So that can be helpful if you're graphing some of these problems from your homework. You can compare them to that chart and see if they would pass a vertical line test or not. So practice these problems. The graphing ones should be fairly straightforward. The ones where you're dealing with an equation and you're trying to solve the equation for y and determine if it's a function or not, those can be a little trickier. So definitely practice these problems. And if you have any questions, come on in and see me before school.